All right. I will say good morning to everyone. The sun is just rising here in Nevada. So thank you for having me. I'll talk about favorable structural settings and exploration strategies in rift basins. I'll provide a basic background initially, then talk about favorable structural settings, and then talk about a project we just completed last year called Play Fairway Analysis, where we discovered some new systems. This is a quick view of the McGinnis Hills geothermal area in central Nevada that's now has 3 power plants producing about 150 megawatts. This is actually a blind geothermal system, meaning there's no surface hot springs or steam vents. And so this is the key to expanding geothermal production in this region is finding these blind systems that are hidden in the subsurface. So just a very quick review of the tectonic setting of this region. Folks are quite familiar with extension across the Basin and Range province, but there is a big component of textural shear in the western part of the region. An area called the Walker Lane takes up about 20% of the plate boundary motion. That's shaded in orange here, about 1 centimeter per year motion, and that actually gets diffused into extension in kind of the northwestern part of the Great Basin region, shown by this blue box here, and that accentuates extension, and of course that's favorable for geothermal activity. The Great Basin region is currently has about 25 power plants shown by these purple stars, about a gigawatt of capacity in the region, probably on any given day producing something on the order of 600 megawatts or so. And everyone agrees there's far more potential in the region on the order of maybe 30,000 megawatts or 30 gigawatts. And this just shows power production through time, and it has been ramping up in Nevada and the region as a whole, but we could do much more. We could produce much more. So just a quick, very quick slide in case you're not familiar with a geothermal system. Of course, you have your production wells, and the main recipe, of course, is heat. Permeability, though, is probably a key in some of our rifted areas where high heat flow is not a problem. So we have heat, for example, across most of the Basin and Range province, and so the key is permeability, and of course you need fluids. But the other tricky thing with geothermal is that you need a balance between your production wells and injection wells. Of course, you have to re-inject to replenish the system, but if you re-inject too close to your production wells, you'll cool the system down. So you really need a good understanding of the detailed structural setting and the subsurface. First, where to find where to drill, especially for those blind systems, but also the balance between production and injection once you do find a viable system. So we know that much of the Basin and Range province is very promising for geothermal development. High heat flow, this map just shows temperatures at 6.5 kilometers depth. We have lots of faulting, active faults, quaternary faults, so a very good setting for development of geothermal energy. So why don't we have more energy produced so far? And this is the key, that most of our most of our systems are blind or hidden beneath the surface. In fact, 40% of our known systems in this region are blind, and most of those up till now have been discovered accidentally with agricultural wells, or maybe well or drill holes for mineral exploration. So these cross sections on the left just kind of illustrate the problem. We have hot fluids coming up along faults, and most of the systems in this region are fault controlled, but generally those fluids hit permeable layers in the subsurface in your basin, and they leak out along those permeable layers, and sometimes they'll surface in hot springs, maybe many kilometers away from the main upwelling. So you drill over here and you're in for a big surprise if you drill on top of the hot springs, because it will cool down with depth, or the systems are just completely hidden where the hot fluids do never surface in any hot springs or steam vents. So it's estimated that about 3/4 of the systems in this region are blind or hidden. And of course, this presents significant drilling risk. And what we need then is high quality geologic geophysical data and good modeling of the systems. And that starts with modeling of the known systems. And then this just illustrates this photo, the tricky part about production and permeability. This is only a couple hundred meters apart. These two wells here, and this is a productive well, meaning you had high heat and permeability. This was a non-productive well just a couple hundred meters away where you have plenty of heat, but you lack permeability. So you really need to, again, understand the details of the structure. So what we did initially was try to review all the known systems in the region, which there's 450, and basically catalog the structural setting that the known systems lie in. We were able to catalog about, well, more than half of those systems. And we quickly found that most systems do not lie along the major segments of faults, the major range front faults. Instead, they occupy structural settings on kind of less conspicuous faults, sometimes associated with the major faults. For example, the most common 4 structural settings that account for about 90% of the known systems are the horsetailing ends of major normal faults, stepovers in normal fault zones, fault intersections, and then accommodation zones where, of course, multiple faults kind of intermesh, oppositely dipping faults, and terminate and intersect at depth. And then as we move westward in the region toward that region of transtension, we pick up a couple of additional structural settings, something we call displacement transfer zones, where a major strike of fault simply terminates in an array of normal faults, and of course this classic pull apart in a strike slip fault system. So these 6 settings account for nearly all of the known geothermal systems in this region, and there's been similar findings elsewhere in rifted areas elsewhere in the world. Kuritz and Carson did a great early study in the 90s. We did some work in Western Turkey, and of course, a lot of work has been done in other regions like the topovolcanic zone of New Zealand. So similar findings elsewhere. So this was a structural perspective, but of course, structure alone is not going to necessarily find a viable geothermal system. You've got to combine that with good geophysical data, good geochemical data, and so on. And so we entered into a project in 2014 funded by Department of Energy in the US called the Play Fairway Analysis, where we combined multiple parameters and we produced a geothermal potential map here for about 96,000 square kilometers. So this was a phased approach. The first phase was taking all of the existing data to produce that map. Second phase was detailed studies of 5 promising areas within that region. And the third phase was, well, if you really think you have it right, we're going to give you some money to drill a couple of areas to try to prove out the methodology. So we chose this transect for a number of reasons. Of course, we have high heat flow, abundant quaternary faulting, and I may not have mentioned the favorable structural settings. The key is also that you have active faults, quaternary faults. And furthermore, across this box, we also had 14 operating geothermal power plants and 34 known systems with temperatures of 130 C or above. And 130 C was our cutoff because that's the temperature at which basically you can produce electricity in a binary power plant, plus or minus, of course, depending on permeability and fluid flow, but that's kind of the average temperature that one might look at for electrical production. And so these were the components we integrated into our Play Fairway analysis. We broke things down into local permeability, where we took into account the favorable structural setting, the recency of faulting, quaternary slip rates, slip and dilation tendency along those quaternary faults, something called intermediate permeability. And that's basically all of the quaternary faults in the region, because we didn't have enough detailed mapping maybe to pick out all of those favorable structural settings. So we simply did a map of all the quaternary faults, did a 500-meter buffer around those faults to account for possible favorable structural settings that we were missing, and then regional permeability, where regional strain rate, earthquake density, quaternary slip rate again, recency of faulting, horizontal gravity gradient, slip and dilation tendency analysis. There are other data sets we would have liked to have included in this. For example, we ended up not including magnetotelluric data because we did not have enough data coverage across the region. Anyways, we combined all of these permeability factors into a clever term called combined permeability. We then combined that with heat, and that was our play fairway. So these are some of the maps we produced: regional permeability, intermediate permeability, just all of the quaternary faults in the region, something we call local permeability, which is basically rating those favorable structural settings, of which there were about 300, covering about 10% of the region. Across this region, I call these measles of opportunity, because it looks like the area has measles. And then all of that, all of these three maps were combined into combined permeability. That produced our play fairway map, combined permeability plus heat. And then we picked out about 25 promising areas in this region. We kind of ranked them in sort of a down select process. And we came up with these 5 areas that we would then conduct detailed studies in. And so the detailed studies included detailed geologic mapping, geochemical studies, shallow temperature surveys, LIDAR, gravity, seismic reflection analysis, if we had those data, slip and dilation tendency analysis on a local scale, also 3D modeling, and ultimately select drilling sites. So I don't have time to go through all of these.
You have 3 to 4 minutes left.
Okay, great. I'll just quickly review Southern Gabbs Valley. These 2 areas on the left here were the areas that moved into phase 3 of the project, where we did selective drilling, temperature gradient drilling. And we found 2 new blind systems. So Southern Gabbs Valley, I should give credit to a master student of mine, Jason Craig, who did much of this work. Basically, we identified a displacement transfer zone in this region, a major strike slip fault terminating an array of normal faults. We went out there. Luckily, there was nothing there, no previous geothermal exploration. And those of you who have been to Nevada, is truly nothing out there except desert. We went there. Luckily, there was a ranch in the middle of the valley. We sampled the wells, the agricultural wells. Indeed, they were warm. We then did some geothermometry on that, and it looked like we had a promising system. And so then we went, excuse me, in and did detailed studies, detailed mapping, detailed gravity survey, detailed mag, shallow temperature survey, 2-meter depth, slip and dilation tendency analysis, and everything was coming together to suggest that this area right here, where there's a 2-meter temperature anomaly, intersecting gravity gradients, a mag low, was favorable for a blind or hidden geothermal system. This is just showing close-up intersecting gravity gradients, indicating intersecting faults at depth, mag low indicating altered rocks at depth, low resistivity anomaly indicating possibly a clay cap at depth, which is why the system may be hidden, 2-meter temperature anomaly. We went in and drilled. This is what the area looks like. We drilled and we hit 124 C at 150 meters depth. So a nice success, and there was another area similar to this too that we were successful at. So, and this just shows the temperature gradients for the 6 wells that we drilled. And then quickly, phase 1 versus phase 2 results. This is the blob, if you will, that we defined at first, that displacement transfer zone. We then went in and did more detailed work. The geophysical data sort of brought the subsurface of the basin to light, and this is what we ended up focusing on. And then this just indicates that's the initial blob. Blue areas are where the favorability went down, put the geothermal potential down. Red areas are where potential went up. So this just emphasizes that you can start with that regional perspective, but you need the detailed data to really understand where to drill, and to minimize the risk in drilling. I'm probably about out of time, so I won't read all these conclusions, but just a really promising region for further geothermal development. About 4 favorable structural settings account for 90% or so of the system. The main challenges, of course, are finding permeability, and play fairway analysis provides a methodology at multiple scales to find these new blind hidden systems and reduce the risk in drilling. And we've just recently been funded to expand this to the entire Great Basin region. So thanks very much.
Well, thanks so much.
Mm-hmm.
You're right on time, no worries.
Oh, good, good. Excellent.
So we have time for a few questions. I said you don't have to type the entire question in the chat. You can also just post a Q so we know to give you the word, or you raise your blue hand and I can see you in the participant list. One thing to maybe to kick this off, this is extremely detailed. I'm really impressed with the amount of data that you have used. What is the time investment for this versus what you finally get out from that you will have a successful drilling versus randomly, sort of have a fair idea of where you would be putting your well and then accepting that some of them will be non-productive?
Sure. Yeah. So that play fairway analysis project started in 2014. Prior to that is when we did the favorable structural setting project. So in that favorable structural setting project was about a 3-year time span, about almost $1 million investment in that. Actually a little less than that, about 700K, I think. And then the 5-year play fairway analysis project, each phase was about 1.5 years or so. And so we reached the point, we were hands tied behind our backs in the first phase because Department of Energy said you cannot acquire any new data. Okay, so we just had to work with existing data. So that was a 5-year project, and we're 2 for 2. So in discovering 2 new systems, and we're of course recently funded to expand that. So I'm trying to bring back my screen and see the chat, but I somehow lost that part. So
right, yeah. It's really impressive the amount of data you've used. There is a question from Martin May. Martin, could you ask it?
Yes, sure. A very interesting talk. I really enjoyed it, James. So sort of following up on what Susanna has been asking, what would you consider the minimum set of data that you would need to come to such detailed mapping? In other words, you said you left out magnetotellurics. What else could you leave out? To come to some useful, let's say, base mapping that allows you to make educated decisions.
Yeah, very good question. And you work with as much data as you can. On the regional basis, something critical we left out in the initial project because we did not have a good, robust regional data set was regional magnetics, and we're now including that. And of course, regional gravity is important. I guess could you leave? I don't think you can leave out structure. Okay, structural, is critical, and of course, the detail with which you can identify the structure will depend on the region. Right, in Indonesia, much more difficult to define structure because of vegetation and so on. And in other regions, anywhere you have these data gaps. So I would just say this: we have taken this show on the road, if you will, to do capacity building, a project led by Bridget Ailing here at the university, and conducting this in Argentina and Peru, and we moving on to possibly Vietnam. And we do the best we can with the data that we have. But I think the fundamental data that's important are enough data to define where your major faults are, active quaternary faults, to try and define those favorable structural settings, and geophysical data of some sort by which to identify those settings, especially in areas, we are fortunate here in Nevada because it's very arid and you can see these structures, but it's not so obvious in much of the world. So some form of geophysical data is important, some form of geochemical data is important, and then boots on the ground, some form of structural data, quaternary fault data. I hope that helps.
Oh yeah, very good, thanks. I'll get back to you via email.
Very good, okay.
We'll take one more last question. I'm aware that we're running a bit late. So August, you had a question?
Oh yes, well thanks for the great talk. I'm interested in the Western Anatolia and the basin range comparison, which is quite fascinating and very similar structures. I'm wondering if there's any interesting development can be made through these low-angle detachment fault surfaces. And many of those faults that you showed were the high-angle ones, which is the margin faults of these graben systems. But you haven't mentioned much, maybe I missed something. But this is something that may be interesting to explore because those are the deep ones that potentially bring hydrothermal circulation, etc.
Yeah, I've worked in Western Anatolia as well. In some cases, the detachment faults become conduits because there's permeable breccia and so on along them. But in general, I really key into the slip and dilation tendency analysis and what faults are favorable to accommodate fluid in the current stress field. And so that's generally your higher angle faults as opposed to your detachment faults. So I think, I guess I might be biased on this, but in my opinion, detachment faults can be passive accommodators for fluid flow in certain cases. There's an example I know of in the Geddes Graben, for example, in Western Anatolia, but they're not the main conduits bringing deeply circulating fluids up from depth, in my opinion. Maybe if the detachment is active, currently active, maybe there's some possibility there. But you think about it, it's not going to be favorably oriented to accommodate fluid flow in a stress field. And something I didn't mention is, of course, the reason that these 4, 5, 6 structural settings are particularly conducive to fluid flow is stress is not relieved on major earthquakes because there are the fault terminations or fault stepovers and so on. So the stress is concentrated there, and furthermore, breccia is more common in these areas where you have multiple sort of minor faults versus a major fault, meaning you have a lot of permeable fault breccia, but not impermeable clay gouge. And so I think major faults can be an impediment to deep circulation. Doesn't mean you can't have a permeability barrier and a spring along that fault, but generally you're going to have cold springs versus hot springs.